Assalamu alaikum and good day. My name is Dr. Farhana. For today's lecture, we will learn about process scheduling, which is an essential part of operating systems that ensures efficient and fair management of multiple processes. This chapter will teach us about the principles, algorithms, and complexities of process scheduling. By the end of this chapter, you will understand how different scheduling algorithms work, their advantages, and how they are used in the real world. In this chapter, we will learn about the basics of CPU scheduling, the criteria used to evaluate scheduling algorithms, and the different scheduling algorithms themselves. In section 5.1, we will introduce the fundamental concepts of CPU scheduling, such as the ready queue and the CPU burst. In section 5.2, we will discuss the different criteria used to evaluate CPU scheduling algorithms, such as fairness, throughput, and turnaround time. In section 5.3, we will learn about the different CPU scheduling algorithms, such as first come, first serve, shortest job first, and round robin. We will discuss how each algorithm works, its advantages and disadvantages, and how it is used in real-world operating systems. Our goals for this chapter are to introduce CPU scheduling and to provide a comprehensive overview of the different CPU scheduling algorithms. We begin with section 5.1, Basic Concepts. Introduces the foundational ideas of CPU scheduling. Multiprogramming allows multiple processes to run in memory at the same time, which maximizes CPU utilization. When one process is waiting for I/O, another process can use the CPU, keeping it busy. A significant majority of processes follow a distinct pattern. Most processes alternate between CPU and I/O operations. A CPU burst is the time when a process needs to use the CPU to run its instructions. This includes operations like loading, storing, and arithmetic calculations. After a CPU burst, a process may need to wait for an I/O operation to finish, such as reading from a file or waiting for user input. This idle time is called an I/O burst. Processes alternate between CPU execution and waiting for I/O in a cycle. This cycle is fundamental to understanding how processes behave in multi-programmed systems. In addition to understanding the CPU I/O burst cycle, it is also important to understand the distribution of CPU bursts. This means understanding how long CPU bursts typically last and how often they occur. This information is essential for designing and implementing efficient scheduling algorithms. The diagram shows how most running processes alternate between CPU bursts and I/O bursts. To better understand the CPU I/O burst cycle, let's look at a simple C program example. The C program snippet on this slide illustrates the alternating CPU and I/O bursts that we discussed earlier. Let's break down the code and see how it demonstrates CPU and I/O bursts. The first two lines of code are an I/O burst because they involve interacting with the keyboard device. The first print function prompts the user to enter an integer. The scan function reads the user's input from the keyboard. This is a clear example of an I/O burst, as the CPU is on hold waiting for the input operation to complete. This arithmetic operation is a CPU burst, as the system is crunching numbers and there is no waiting for external input or output. The final printf function prints the result to the screen. Like the first printf function, this is also an I/O burst. In this slide, we will now look at a histogram of CPU burst times. This histogram comes from the textbook, and it gives us important insights into how processes behave in the CPU. Let's understand the histogram. The horizontal axis or x-axis shows how long each CPU burst lasts in milliseconds. The vertical axis or y-axis shows how many processes have each burst duration. The histogram shows the following. Many processes have short bursts. This is shown by the high peak at the beginning of the graph. Most processes have bursts that are less than 8 milliseconds long. This means that many processes finish quickly. Fewer processes have long bursts. This is shown by the sharp decrease in frequency as we move to the right on the graph. The frequency of processes with longer bursts decreases sharply as we move to the right on the graph. This means that there are fewer processes with long bursts. What does this mean for scheduling? We need to understand the distribution of burst times to design good CPU scheduling algorithms. If most processes are short-lived because of the pattern in the histogram, we want a scheduling algorithm that can handle a lot of short tasks without making the longer tasks wait too long. Next, we will discuss the different states that jobs and processes can be in and how they transition between these states. Jobs move through the system, changing from one state to another. This reflects the different stages of their life cycle. The job scheduler, also known as the long-term scheduler, decides which new processes to admit into the system from the job pool. When the system is not too busy, the job scheduler will admit more jobs. But when the system is busy, the scheduler may not admit any new jobs. On the other hand, the CPU scheduler, known as the short-term scheduler, decides which of the ready processes in memory will be executed or run next by the CPU. Let's look more closely at the different process states and how they transition between each other. First is new state. Processes that have just been created but are not ready to run are in the new state. Second is ready state. Processes that have been loaded into memory and are waiting to be executed are in the ready state. They are ready to run but are waiting for the CPU. Third is running state. Processes that have been selected by the CPU scheduler are in the running state. This is the state where processes are actively executing. Fourth is waiting state. Processes may enter the waiting state if they need to perform an eye or operation or wait for a specific event to occur. For example, a process may wait until the required page is loaded into memory if a page fault occurs. And the fifth is terminated. Processes that have finished executing or have been terminated by the operating system are in the terminated state. Look at the arrows in the diagram. They show how processes transition between states. The job and process scheduler controls processes as they transition from the new state to the ready state, and from the ready state to the running state. The running process transitions back to the ready state when the CPU scheduler triggers an interrupt. When the process requests an eye or resource, it is moved from the running state to the waiting state. Once the eye or request has been completed, the process is returned to the ready state. Only processes in the ready state are eligible to be executed by the CPU. Once a running job or process completes its execution or encounters an error, the job or CPU scheduler will terminate the job or process. We will continue our discussion of job and process status by focusing on the transitions that a job undergoes after it is submitted by the user. Understanding these transitions is essential because they show how the operating system manages multiple processes in a systematic way. The life cycle of a job begins when the user submits it. A job can be either batch or interactive. When the user submits a job, the system accepts it. The job is then placed in the hold state and queued for processing. The hold state is a temporary stop where the operating system can manage resources and decide when the job can move to the next state. The job state changes from new to ready. This means that the job is in line and waiting for the CPU to run it. This transition is important because it shows that the job has been initialized and loaded into main memory, which means it is ready to be executed. Once the CPU scheduler selects the job, it moves from the ready state to the running state. This is when the job actually starts running its tasks. Not all jobs can go from running to completion without stopping. Some jobs may need resources that are not currently available, or they may need to wait for events like I or operations to finish. When this happens, the job moves from the running state to the waiting state. This means that the job has temporarily stopped running until the conditions it needs are met or the resources it needs become available. The final stage in a job's life cycle is the terminated state. This is when the job has finished running, whether it was successful or not. It is important to note that termination does not always mean success. A job can terminate unsuccessfully due to errors, lack of resources, or other reasons. The journey of a job from submission to termination is a systematic progression through different states, each with its own importance. The operating system schedulers control these transitions to ensure that resources are used optimally and that processing is efficient. Learning about process states and their implications is crucial for anyone who wants to understand how an operating system manages processes. In this slide, we will explore an important part of the process management system, the process control block or PCB. PCBs are essential for organizing, tracking, and managing processes throughout their lifespan. This slide will explain what PCBs are, what they do, and how they relate to process queues. When the operating system accepts a job, it creates a process control block for that job. The PCB contains information about the job, such as its state, CPU registers, memory allocation, and I/O status. The PCB is updated as the job progresses. Queues use PCBs to track jobs. Queues exist for the ready, running, and waiting states, and the PCBs are the entries in these queues. The PCB contains important information about the job, such as its state, CPU registers, memory allocation, and I/O status. This information allows the operating system to efficiently manage, pause, and resume jobs without losing any context. The PCBs are linked together to form the process queues. The jobs themselves are still separate entities even though the PCBs are linked together. This structure allows for the organized management and scheduling of processes. The operating system uses different scheduling policies to decide which job in the queue should run next. These policies are designed to improve performance, maximize throughput, and ensure fairness. In this part of lecture, we will focus on a crucial component of process management, the CPU scheduler. The CPU scheduler is responsible for deciding which process gets to use the CPU next. The operating system is responsible for making sure that the CPU is always busy when it is not idle. It does this by selecting a process from the ready queue to run next. The CPU scheduler is like a maestro directing an orchestra. When one instrument finishes playing, the maestro tells the next instrument to play. The CPU scheduler looks at the ready queue and decides which process to run next. It may seem like the best way to organize the ready queue is first come, first serve, but this is not always the best approach. The ready queue can be organized in different ways, depending on the scheduling algorithm being used. Some algorithms prioritize shorter jobs, while others focus on process priority or even use a round-robin approach. CPU scheduling decisions are not only made when the CPU becomes idle. Here are some other circumstances where CPU scheduling decisions are made: running to waiting. If a running process needs to wait for an I or operation or another event, the CPU scheduler will select a different process to run. The current running process will be moved to the waiting state, allowing the selected process to utilize the CPU resources. Running to ready state. In preemptive scheduling, the CPU scheduler can interrupt the currently running process and switch it back to the ready state, allowing another ready process to start using CPU resource. Waiting to ready. A process in the waiting state becomes ready because the conditions or resources it needs are now available. The CPU scheduler then decides which process from the ready queue should run next. Process termination. When a process finishes running or is terminated, the CPU scheduler decides which process from the ready queue should run next. We have already learned about the CPU scheduler. In this slide, we will discuss a specific type of scheduling algorithm, non-preemptive scheduling. Non-preemptive scheduling is different from preemptive scheduling in the way that it decides which process gets to use the CPU. The CPU scheduler does not have any choice in situations 1 and 4. In situation 1, the running process needs to wait for something, so it moves to the waiting state. In situation 4, the running process has finished its task, so it terminates. In both cases, the CPU scheduler must run the next process in the ready queue. This shows that non-preemptive scheduling is a non-discretionary algorithm. Once a process is given the CPU in non-preemptive scheduling, it gets to keep the CPU until it finishes its task or needs to wait for something. This is different from preemptive scheduling, where a process can be interrupted by a higher priority process. A process in non-preemptive scheduling only gives up the CPU when it finishes its task, needs to wait for something, or voluntarily switches to the waiting state. Non-preemptive scheduling is easy to understand and implement. It also reduces the overhead of context switching, which can improve performance in some cases. However, non-preemptive scheduling is not very flexible. A long process can monopolize the CPU, which means that other processes have to wait longer. In our next slide, we will learn about preemptive scheduling to get a better understanding of CPU scheduling strategies. Having learned about non-preemptive scheduling in previous slides, let's now discuss its opposite, preemptive scheduling. Preemptive scheduling allows the operating system to take the CPU away from a process that is currently running, which makes the system more flexible and dynamic. Preemptive scheduling gives the operating system the ability to choose which process to run in situations 2 and 3 that have been discussed in CPU scheduler slide. Unlike non-preemptive scheduling, which has a strict no-choice policy in situations 1 and 4. This allows the operating system to react more quickly to changes in the system, such as the arrival of a higher priority process or changes in process state. One of the main challenges with preemptive scheduling is race conditions, which can occur when processes share data. For example, if process is updating a piece of data and is preempted to allow process B to run, and process B reads the same piece of data, the data may be inconsistent. This can be a problem for processes that require their operations to be atomic or absolutely consistent. Preempting a process in kernel mode can cause the system to become inconsistent, especially if the kernel is managing important system resources. This can lead to cascading failures that make the system unstable. If an interrupt occurs while the operating system is performing a critical task, and the operating system needs to switch context, the results can be unpredictable. It is important to handle these interrupts efficiently to maintain system robustness. Most modern operating systems, including Windows, Linux, macOS, and Unix, use preemptive scheduling algorithms. This is because preemptive scheduling is effective at managing multitasking environments efficiently, even though it has some challenges.